Okay, so I think it's recording.
Okay, so we're good to start, and to everyone who's joined today, it's really nice to see you, and we are inviting today Marc Jolivet to give a presentation on his work looking at the Mesozoic and Cenozoic tectonic, topographic, and climate evolution of the Tianshan region, an insight from geomorphology and sediment analysis. Just to give you a little bit of a background introduction to Marc's career. He's a CNRS researcher in Geosciences Rennes. Did his PhD jointly between University of Montpellier, IPG Paris, and ETH Zurich, using fish and trap Thermo Chronology in North and Tibet. Mainly interested in paleolandscape evolution in association with tectonics and climate, using multidisciplinary approaches, structural geology, geomorphology, sedimentology, and thermochronology. Very interested in Central Asia, anywhere from Siberia to northern Tibet, and has about 15 years of working in such regions. He's also developing research interests in southern Africa, looking at the planation of the South African plateau. Before I just hand over to Marc, just to say that this is the third of the talks that we're running within this sequence of lectures with the theme of Central Asia and the tectonics or earthquake hazards of Central Asia. Marc has put on the little logo at the bottom. This is kind of something that we started as part of a kind of a consortium project funded by the NATO Science for Peace and Security program. This is looking at environmental security, paleoseismology, earthquake hazards, the effects on cities, infrastructure, transport links, etc., within the countries of Kyrgyzstan and Kazakhstan. We began that last summer. Obviously, we had to postpone a lot of the field work, and there's also lots of training and other such activities planned, which have been pushed back by a year or so. And so what we've concentrated on doing over this past year is to kind of build a lot of community-led activities, one of which is this lecture series, so that we all get to know a little bit more of what we are doing and to learn from each other and to build this network. Hopefully this is something that will continue as well. We've been doing them every 2 months on the last Monday of the month, right? So you notice the link there. The next one would be due to be in the end of August, but a lot of us are field workers. I imagine that's actually going to be not the ideal time, so we'll probably skip through until the following one. So we'll take a break over the summer and then rejoin us for autumn. You can get updates on what the program is doing through our website, Quakes in Central Asia. Also on Twitter as well, right, where we advertise these talks. So and also on the website, I should mention, we upload the talks afterwards. Marc has kindly agreed for us to upload that, and we have 2 previous ones, Ray Weldon, and also on the Permian plateau as well. They are all on the line, and then you will be able to see Marc's as well from tomorrow onwards. So thank you very much, and I'll hand over to Marc.
Okay, thank you, Richard, and thank you, Magali and Christophe, for inviting me to give this talk. So the earthquakes in Central Asia group is mostly focusing on the neotectonics activity of Kazakhstan and Kyrgyzstan. But today I want to go back a little back in time, say something like 200 million years, to show you that the Mesozoic and some part of the Cenozoic tectonic, topographic and climate evolution in the Tianshan range is going to set up the path for the present day topography. And to do that, I will use geomorphology, of course, a lot of sediment analysis, and a little bit of thermo chronology. This work is, of course, a collaborative work, and I would like to thank all the PhD students that work with me on this project, as well as my colleagues here in France, in China, Kyrgyzstan, and Belgium. sorry. So the present day topography of Asia is very complex. As you all know, we have a big mountain range like the Himalayas, for example. We have plateaus like Tibet, some ranges far away from the collision zones. We also have big basins like the Tarim and Junggar here in Western China, but also the Ordos or Sichuan basins. And in between those ranges and basins, we have a medium altitude topography here, which is very characteristic of the eastern part, mostly of Central Asia. And the aim of this talk is to understand how much of that topography is of Cenozoic origin and how much is inherited from previous geodynamic events. So if the topography of Asia is complex, the lithospheric structure of the continent is also very complex. Here you have a map of the main blocks that are forming this continent. It's especially detailed here around the Tibet plateau. As you can see, there are some about a few tens of blocks everywhere. Here I did not put into details inside the Central Asian orogenic belt, but this is again a collection of tens of small blocks. And of course, all those blocks are separated by lithospheric structures that are forming a weak zone in the crust and in the lithosphere, which are going to localize most of the deformation during the Mesozoic collision events and during the India-Asia collision, of course. So the main geodynamic events that are going to be of interest in this talk today are starting in the late Carboniferous, early Permian, with a huge strike-slip event here along faults that are now in the Tianshan region. And the blocks here, Tarim, Mongolia, and North China are going to move about 1,600 kilometers compared to Siberia and Kazakhstan. And these big shear zones are still active in the Tianshan. For example, the Talas-Fergana fault here that we are going to talk about later, and the so-called Nikolaev line here separating what is now the Tarim from the Kazakh plate. Going up in time, we reach the late Permian, early Triassic, and we have now the closure of the Paleotethys Ocean here, which is now in Tibet, and the docking of the big Tiantang and Sibumasu block here. Tiantang is now forming the central part of Tibet, and this collision has a lot of impact in terms of tectonic and relief building on the central part of Asia here. Reaching the Jurassic now, middle to late Jurassic, it seems that nothing happens. In fact, we have a subduction zone all around the continent here. We have a little bit of extension in the South Caspian Basin and in general in the Turan plate. The Lhasa block or the West Burma blocks here are quite far away to the south. So it looks like it's a very quiet period. In the early Cretaceous, we have the accretion of the Lhasa block here, but we have no evidence of large deformation of or topographic building associated to that, and I will come back also to that later. So one good way to look at the age of the topography, of the continental topography, is to use Thermo Chronology, mostly apatite fission tracks and apatite uranium, thorium, helium. For those of you who are not familiar with Thermo Chronology, it allows to follow the thermal path of the rocks for the fission tracks in a temperature range of about 120 to say 60 degrees. And if you are lucky enough to have some uranium, thorium, helium on the same apatite, you can go up to say 50 degrees. I'm a little bit optimistic here with my 40 degrees. So this gives you the cooling pattern or the reheating pattern for some times between 4 and say 2 to 1.5 kilometers. If we look at the basement rocks older than Triassic, here is a compilation of fission track ages I made in 2015, so there might be more ages now, of course. What we have is a cloud of data, a cloud of ages. There is no real pattern in there. we go in age from 0 nearly to something around 360 million years. And all the altitude range is represented from 0 here to 5,500 meters without obvious pattern in the distribution. Sorry. When we superpose to that the main orogenic event, of course, a lot of those ages are falling within the collision time of India, here between 50 and 0 million years. Many samples here. But if we go to the Lhasa collision, for example, here, of course, we have some samples there, some ages there, but there is no characteristic peaks or anything. It seems that they are part of the cloud we had before. If we go to the Tian time, we only have a few samples. And the message from that is that there is no real correlation between the ages and the orogenic events, except, of course, for India. However, now if we look at the topography in the areas where those samples were taken, there is now a direct relation between the topography and the ages. As you could expect, the youngest ages have been sampled in these very steep topographies, alpine type topographies of the young ranges. This, for example, is the Longmen Shan here in eastern Tibet, the Dadu River gorges with a total relief of about 5,000 meters and very steep slopes. However, as you can see here, in those ranges, even if the exhumation is very rapid, you still preserve some quite old ages. These ones are late Cretaceous, early Paleogene. So this is, again, a mixture between young ages and oldest one. Now, if we go to the very old ages here, above 100 million years, they are systematically associated to this kind of topography. Here is the Khamardaban Plateau in the Shan ranges, south of the Baikal Lake. There are very flat areas, flat topography, poorly incised. And this plateau, for example, is about 2,000 meters high. So there is a direct correlation between topography and fission track ages in Asia. Now, if we focus on the plateau areas, they all have the same thermal history, more or less. You find them everywhere from the eastern Tibet here, for example, in the Yidum or Sampangase area, in the Kunlun, in the Tianshan, we're going to come back to this, in Mongolia and in Siberia. And as you can see here, this is the cooling path obtained from fission tracks or multiple geochronology analysis. And you see that they all show a very more or less rapid exhumation here in the late Triassic, early Jurassic for some of them, and then a very long stay here at the same temperature for about 200 to 150 million years. If we go to Tianshan, we have the same sort of pattern. We have exhumation in the middle to late Jurassic, then nothing happens until the Cenozoic. The only place where it's a little bit different is here in Siberia, the Oka Plateau, where we have a very slow erosion through time. But I have to mention that the data here were not of very good quality, so I will be careful in using these samples. What it means that to get this isothermal stage, you need to have no tectonics and no erosion because you would be cooling the samples, and you need to have no sedimentation. So the question is, did we really stay for 150 million years without vertical movement and without sedimentation? Here to the left is a diagram by Todd Ellis and Ken Farley that I really like. They mostly show that although Thermo Chronology is useful in mountain ranges, it is largely blind to decipher the surface, the detailed surface morphology. What they did is they generated a topography with a total relief of about 4,000 meters here between point A and point B. And they tried to image this topography using the uranium thorium helium data and using the fission track data. And if we take the gray surface here, which is a fission track data on apatite, you see that the maximum relief you get is 400 meters. So Fission Tracks is seeing 400 meters and the reality is 4,000 meters. So it's very difficult to image surface topography with those thermochronometers. So the idea of the project was to use, of course, basement geology to get the long-term general evolution of the surfaces and of the ranges, using geochronology, thermochronology, structural geology, or geomorphology. But to combine this with sediment analysis in the basins, mostly facies, depositional environments, fossils, and so on, to get the paleo environments, the paleoclimates, and the paleo drainage. And probably the best place to do that in Central Asia is the Tianshan range here. So this is an intracontinental range squeezed between the Kazakh and Junggar plates to the north and the Tarim Craton to the south. And Tianshan has remained in a semi-arid climate for a long time. We're going to see that later. And we have a big desert area like the Tarim and Junggar. Here you have a picture of the Junggar desert. We have a fantastic sediment record, especially in the northern Piedmont and southern Piedmont here. Here is the Anji River. We go from Carboniferous sediments to Quaternary sediments without any interruption. And of course, we have access to the basement in the range. Here is the Arbinshan in the Bayan Bullock Basin. So a perfect setting to mix basement geology and basin geology. Here is a cross-section I've tried to draw between the Altimtag, so the northern part of Tibet, and the Altai range on the other side, across the Tianshan and across the two basins. And you see that both the Tarim here to the south and the Junggar to the north have a very thick and nice sedimentary record from Permian here in the Junggar up to the Quaternary, and from mostly Triassic a little bit and Jurassic here to Quaternary in the Tarim. However, both basins seem to have a very different history, especially in the Jurassic. You have here an isopac map drawn by Julien Morin of the Tarim and the Junggar. And as you can see, the Junggar is has a very deep depot center here in the south, near the Tianshan range, with a thickness up to 8 kilometers, I think, of Jurassic sediments. While the Tarim Basin looks like a sag with a little bit of subsidence here to the north, up to 3,000 meters. And most of the western part of Tarim is either in erosion or bypass. In the Cenozoic, the situation is quite different. Both basins are subsiding. We go up to 10 kilometers of sedimentation in the Tarim here near the East Kunlun. The West Kunlun, sorry, and the Junggar is also very deep, something around 7 kilometers here. And both basins are very similar in terms of dynamics. Okay, so let's have a look at the Jurassic and Cretaceous Tianshan first. To decipher the paleotopographic and paleoenvironment evolution of the range, we logged a series of sections here in China and some here in Kyrgyzstan, focusing on the Mesozoic, so mainly Jurassic and Cretaceous. And this is where the students have been very, very useful, because they logged all those sections. If you look here, for example, the Manas section, which is a reference, we have 5.2 kilometers of Jurassic sediments just on that section. On each of those sections, of course, we get the log. We also try to derive the paleo depositional environments for all of these. You have the Fisher diagram for all of them. We got the pollens, the fauna, some of them including dinosaurs here in Kyrgyzstan. We got the paleocurrents as much as we could, and the provenance studies. So I'm going to focus here on the Manas section, which is our reference, but you can imagine that most of the sections show the same story, in fact. So we start here in the late Triassic, very early lower Jurassic, with big alluvial fans here. There are conglomerate built alluvial fans with a lot of plant remains. Here you have a piece of a ginkgo biloba trunk. So probably a very humid climate. And we're at the end of the dismembering of the Permian topography. You remember the strike slip event in Permian. We built up a huge topography, probably something similar to what we have now. And in the late Triassic, we're just finishing to destroy that topography, and we still have some relief producing a lot of coarse sediments. When we go up into the middle Jurassic, we still have a lot of plants, so still a humid climate. We don't know if it's hot or cold, but it's humid at least. But the sedimentation is quite different. We now have a wide alluvial plain with sandy bodies here, which are channels, and overbank deposits, which are muddy, fine-grained sandstones and a lot of coal. Okay, so it seems that the topography we had in the Triassic has now disappeared. It's eroded away, and we have flat, probably relatively distal alluvial plains. Now, if we look at the substratum of those Jurassic sediments, we see, especially here in the Terrim, that they are deposited directly on the Paleozoic basement. This is a nice section in the Terrim basin drawn by Laval and collaborators. And as you can see, there's a bit of Triassic on top of the basement. Otherwise, the Jurassic is sitting directly on the basement here. And it's mostly the same in the Jungar basin. Now, if we look at the shape of that Jurassic surface at the base of the Jurassic sediments, here is what we have. This is a picture taken by Stéphane Dominguez, I think, from the Bororo range. When you arrive in Urumqi by plane from Beijing, you follow the Bororo, and you can see this very fantastic flat surface here sitting on the top of the mountain. And if you look in detail on top of that surface, you still have some preserved topography here. And the top of that topography is again flat. So it's a series of flat surfaces. Here is a DEM of the same mountains, of the Bogda. And you can see this pale orange area here is the planation surface at 4,000 meters. And we have a 1.5 or so remaining topography on top of that, with again a flat plateau at the surface. We have the same thing if we move further west into the Bororo range, west of the Jungar basin. Again, a flat surface here. This one is at about 2,000 meters high or so, and some remaining topography on top of that surface, again, nearly 1 kilometer here. And that surface here is covered by lacustrine sediments, and these are Burdigalian sediments, so Cenozoic ones. If you do fission track analysis on some of those rocks, you get the story I was showing you earlier. So a very slow exhumation here during early to middle Jurassic, and then nothing else happens. And this is a sample taken by Johan de Graaf and collaborators on the Songkul Plateau in Kyrgyzstan, and you see that the planation occurred much earlier, somewhere in the Triassic, and then it remains very flat all the time. So with Julien Morin, during his PhD, we have tried to map those surfaces, and all the red spots here are the main preserved remnants of those surfaces. Some of them are tilted like this. They start to be incised, but they are still recognizable. And Julien has also looked at the sediment that were sitting on top of those topographic remnants to try to give them a minimum age. And this is the result of that study. So the full dark line here is the time of existence of each of those plateaux derived from Thermo Chronology and sediment analysis. And the dotted lines here are the assumed time of formation. As you can see, most of them here formed during the Jurassic, late Jurassic, and were preserved up to now. But some of them, especially inside the Tianshan range, the Gili Basin, for example, or the smaller Nileke Basin, seems to be much older, and they probably start forming during the Permian. On this surface here, we do have some early Triassic sediments, and they are staying on a very flat surface, so we assume it formed before that. One interesting point is that we start to see those surfaces at a very peculiar period here when we go from a humid climate I was describing before on the Manas section to what we are going to see now, a semi-arid to arid climate. And there is probably a direct link between the preservation of those surfaces and the semi-arid climate. Another point is that all those surfaces survived the various orogenic events like the Lhasa docking, the Karakoram-Pamir formation, and of course the India-Asia collision. And for the oldest of them, they also survived the Tian collision. It means that those flat surfaces are able to resist orogeny. Okay, if we now go up in time and we reach the upper Jurassic, there is, as I told you, a drastic change in climate. We now find in the Chigu Formation, for example, those very red beds, and they're full of carbonated paleosoils. This is amalgamated wood cast, and this one is about 1 meter thick, but they can be thicker than that. And the other interesting point is that you see there is a discordancy here, angular uniformity between the Chigu Formation, the Upper Jurassic Formation, and the overlying one, which is the Kalaza Formation. So some evidence here of tectonic movement at the end of the Upper Jurassic. Remember my maps at the beginning, that was a time where it was supposed to be very, very quiet. The Kalaza Formation, here is again the Manas section. It's a very impressive alluvial fan. This one is about 800 meters thick. And inside this alluvial fan, we find a lot of mud cracks. We find a lot of small layers of carbonated sandstones here, which are probably paleosoil. And all this is indicative of arid climate conditions. If we go a little bit further inside the basin, so a more distal section, we still have the red Chigu Formation here, which is a very distal alluvial plain with some small paleosoil. But on top of that, the Kalaza is no more alluvial fan, but it's Aeolian dunes. So we had big, big dunes at the end of the Jurassic early Cretaceous in the Jongar Basin. So we have to imagine something relatively flat with a slightly reactive topography maybe, and some desert conditions. So this is the most arid conditions we have between the Triassic and today, in fact. And this pattern, you find it all around the Tianshan. Here is a Yaha section in the northern Tarim Basin. You find the Chigu Formation again with the paleosoils here, and on top of it, the huge Kalaza conglomerates. If we go to the Fergana Basin in Kyrgyzstan, of course, the name of the formations is changing, but you still have the alluvial plain here, and on top of it, the big conglomerate layers. So from all this data, we, together with Julien, we tried to derive paleotopographic and paleo-environmental maps. And we start here in the early to early middle Jurassic. The brown area is the exposed basement, and the darkest the color, the highest the topography. Of course, this is always relative. We have no value of the altitude, of course. But as you can see in the early Jurassic, we still have a quite high topography, in fact, quite marked one. Small lakes here in the Yeli Basin, lakes in the Junga and the Tarim, so a humid climate, and a relatively restricted alluvial plain environment. When we go up into the late middle to early late Jurassic, the topography is largely reduced. We have a lot of areas here to the north and in the western Tarim under erosion or bypass. We don't know. In fact, there is no sediments preserved on top of them. We still have lakes in the Tarim and Jungar, but the alluvial plain is widening, showing that the lakes are just retreating. The climate is becoming semi-arid, and when we turn to the late Jurassic, early Cretaceous, we have a renewed topography, no more lakes, a lot of bypass or erosion areas, and some big ergs, big dunes inside the Junggar Basin and probably the Terek. And the red part here are the Kalaza alluvial fan. So a complete change between humid climate here since the Triassic to a very arid climate in the Upper Jurassic, early Cretaceous. Okay, I've been discussing the eastern part of the Tianshan, so eastern Kyrgyzstan and western China, but I've not mentioned what's going on west of the Talas Fergana fault. And this is what I'm going to try to show you now. I've put here 3 sections. One you already know in between the Altintag and Altai ranges, where you see those nice compressional basins here with very thick deposits of Mesozoic and Cenozoic. If you go west of the Talas Fergana fault here, I've drawn a section from the Shu-Sarisu basin here to the Kopedag in Iran, and another short one across the Turgai basin here immediately to the north of the Talas Fergana fault. And as you can see, the basins are very different there. It's a completely different tectonic regime. The Turgai basin, for example, in the Jurassic is a series of small grabens, so there's no more thrust faults there. And the Cretaceous is just a sag. The Cenozoic series are very, very limited. If we go to the big section here, as you can see, we always have, we only have normal faults everywhere, a bit of strike slip faulting here in the Kizilkum Massif in the middle. The Jurassic basin is normal fault controlled, and the Cretaceous basin is probably again a sag. The Cenozoic sequence is very limited again. So 2 completely different areas. To try to understand the kinematic of the Yerkan Fergana fault, the Talas Fergana fault, sorry, we went to the Yerkan Fergana basin, which is the only one to be fairly well preserved along that fault and directly linked to the fault itself. So the Talas Fergana fault is thought to be a strike slip fault. It is actually a strike slip fault, and it's supposed to have remained that for all its history. And everybody says that it's the Yerkan Fergana basin is just a pull apart basin developing during dextral shear stress on the Talas Fergana fault. As you can see, the basin is relatively deformed, but the sequences are well preserved. It's a bit difficult to access because there's no road, so everything has to be done on foot. Anyway, with Julien, we just logged several of those sections. The longest one is about 1.5 kilometers thick. And one of the primary goals there was to date the series, because when you take the various geological maps available, the age of the series goes from Triassic to Upper Jurassic. And in some maps, we only have middle and lower Jurassic. So for that, we found some pollens that were poorly preserved. It was difficult to use them, but most of them indicate lower to early middle Jurassic ages for the whole sequence, except here to the south in the Terek section, which is here somewhere, very close to the Fergana Basin, where we have a little bit of Upper Jurassic. So again, from those data, we derived paleogeographic reconstructions of the basin, and we start here in the middle late Triassic, with the flat surface eroded into the basement. And we think the Talas Fergana fault initiated during the early Jurassic, maybe Sinemurian, probably Pleistocene, based on the pollens. And it's not a strike slip fault. We have no evidence of strike slip faulting there. It's a pure, nearly pure normal fault. And the Yerkan Fergana basin is developing as a hemigraben. Most of the sediment input comes from the west, and we have no evidence, or only a few evidence of alluvial fans here coming from the eastern part. The basin widens during the late, early, and early middle Jurassic, and the lake here in the basin becomes very large and very deep. And the sediment input decreases through time, mostly because the topography here on the edge of the basin is very flat. And we start to see a big lake developing also in the Fergana basin. By late Jurassic, early Cretaceous, we have a complete inversion of the basin, and we start developing the equivalent of the Calaza formation, dry climate alluvial fans here on the edge of the Fergana basin, the Yukon Fergana basin being now a positive topography. The explanation we give for these two very different domains on each side of the Talas-Fergana fault is directly linked to the subduction zone here of the Neotethys along the the southern border of the continent. And we think that to the west, the slab here is rolling back, so it's retreating, creating the extension here in the South Caspian domain, the initiation of the South Caspian basin. We also have evidence of extension here in the Kopedag and also in the Amudarya and Sirdarya basin. And in this hypothesis, the Talas-Fergana fault here is a major boundary between the two domains. And here in the eastern Tianshan, we have block rotation and compression, probably due to the final part of the docking of the Tiantan block and some different subduction pattern here, no rollbacks probably on the Neotethys slab. Okay, I'm going to go very briefly on the Cretaceous evolution, just to say that we have no real evidence of topography or deformation linked to the docking of the Lhasa block here to the south. The only small evidence of deformation we could have is the unconformity, the angular unconformity between the Shidiu and the Kalaza formation here, but it's a bit too old for the age of the collision. So it seems to occur before the collision. Here you have two sections, one in Tashkumir in Kyrgyzstan and the Manas section, and you see that most of the Cretaceous series here are describing either alluvial plain with some channels here, gravity channels, or here in the Manas section, mostly a big lake. And then we reach these huge conglomerate layers here in the upper Cretaceous in the Manas sections, and here at the limit between the upper Cretaceous and Paleogene in the Tashkumir section. So just to show you the series, here is a Tashkumir section. You see there are again red beds. So they show semi-arid climate all along the Cretaceous. And as you can see, the series are getting whiter here. And that's because we have a lot of paleosoils developing. So here is an example of just one small part of an outcrop. We have one paleosoil here, another one here, another one here. So they are very, very ubiquitous into the series. And they are formed by carbonated root casts. However, we found a lot of dinosaur nests into those series. Here is a nest of somebody who probably of like an hadrosaur. We have about 8 eggs in there, and we had the nest everywhere on the cliff. So semi-arid alluvial plain, but very, very rich fauna. Okay, now let's go to the Cenozoic Tianshan to finish. And starting to the west with the transgression of the Protoparatethys Sea. So the first transgression occurred during the late Cretaceous, and it barely reached the Terran Basin here. This is a work by Bosboom and collaborators. And as you can see, the Tashkumir formation here, section here, was preserved from the marine invasion, probably because we had a small topography remaining here to the south. The fourth transgression is the main one, and it invaded Terran here, probably going a little bit further than what I draw here, and flooding the Tashkumir section here. And we can see that here we have the big Ypresian sandstones here cemented by carbonates. And at the base of those sandstones, we found a lot of oyster beds. Some of those oysters are quite big, in fact. So here, mostly, again, a flat topography and some marine transgressions. If we go further to the east, in the Chinese Tianshan and up to Mongolia, the Cretaceous Paleogene transition is marked by those huge paleosoil, those huge calcretes. This one is about 8 meters thick. It's a conglomerate completely cemented by carbonate. If we go to the south of the Tianshan, here in the Yaha section, we have these whitish layers. It's about 15 meters thick, and it's again a calcrete. If we go to the Gobi Desert in Mongolia, we again have these calcrete layers here, which are again about 10 meters thick, sorry. And just on top of this layer, we found this Yenodong Zhou, which is dated to the Oligocene. So we know this part of the section is Oligocene. Back to the Yaha section, there was two groups of Chinese colleagues working on that, doing magnetostratigraphy, and one led by Peng was working on the Mesozoic sections, going from the Triassic to as much as possible to the end of the Cretaceous, and they reached the base of this layer with an age of 66 million years. And the second group, led by Wang, was coming from the Quaternary down to as much as possible in the Cenozoic, and they reached the base of this conglomerate layer here with an age of 35 million years. I let you imagine the few years of fighting between those two groups, trying to know who was right, who was wrong, because they only had 15 meters here. But in fact, we show that those 15 meters here represent indeed 30 million years of time. So we have, to do that, we have a very flat area, no sedimentation, no erosion, in fact, nothing happens. And this is how we draw this. We have remnants of erosion surface in the altitude, some topography. The main erosion surface here in the basement, probably incised by small canyons to produce the sediments for those conglomerates, but nothing is moving, nothing is going up, nothing is going down, nothing is deformed. However, we do have some evidence of small tectonic movements on very specific structures like the Narat-Nikolaev line here, where the fission tracks and uranium thorium helium data indicates rapid exhumation around 55 to 60 million years, just at the beginning of the collision of India with Asia. So generally a very quiet, tectonically quiet environment, but some onset of deformation. Rapidly now, the Neogene is of course marked by the uplift of the range. This is a log obtained by Julien Charot and collaborators in the Kwitun Valley, so southern Jungar Basin. And they start here around 23 million years with two lake episodes. So we have big lakes developing into the Jungar Basin. So again, a rainy climate, more humid, and those lakes are going to flood a large part of the Tianshan Piedmont. And these are the Burdigalian sediments we found on top of the eroded surface. Then we see the development of alluvial plain here with more and more conglomerate layers until we reach the Shigyu formation, which is just a huge alluvial fan here on both the northern and southern Piedmont, showing that the topography behind has a very high relief and produce a lot of sediments. So this gives the very peculiar topography of the Tianshan range today with alpine type relief here, for example, in the North Bororo slopes, so the North Tianshan range, steep slopes, very deep valleys here, the Kwitun Valley, and fission track ages around 8 to 10 million years, saying that the range started really to go up around 10 million years. If you go on the other side of these mountains, you find the remnants of those very flat surfaces. This one is tilted now, so it starts to be incised. But when you go down here collecting samples for the fission tracks, you get ages going from 8 million years here to about 275 million years at the bottom of the ridge. Inside the range, the Narat range, for example, here's a flat plateau here around 2,500 meters, again with fission track ages around 150 to 70 million years. So it's a mixture of very old topography and very young topography. Finally, what's on my to-do list for the next trip? Well, we all know the fault thrust here on both sides of the Tianshan. We all know the strike slip faults here inside the range. But if we go here to the eastern part of the Yili Basin, so well inside the range, along the Narat Fault, this is the Narat Fault here running along this line. We see it on Google Earth. If we take a picture from this area here to the east looking west, what we see is the crest of the Narat Ridge here, which is with the flat surface. And we found again this flat surface here, but about 500 meters lower in altitude. And if we look at the limit between those two plateaus, we see those very nice triangular shape facet, one here, one here, one here again. This gives an indication that the Narat fault is indeed a strike slip fault, but it's also a normal fault inside the range. And I was discussing that with Magali. Apparently she found some in Kyrgyzstan also, and they are everywhere around the Yili Basin. So what I would like to do now is to understand the significance of those normal faults inside the range. Thank you. I'm sorry it's a bit long. I will leave you there, and I'm ready for questions if you have some.
Not at all. Thank you very, very much, Marc, for that. It was very interesting presentation. So we probably have some questions. If I may ask people if they were to just put into the chat box that they want to ask a question or type their question in, and then I can kind of keep control of things. While people are doing that, I'll kind of nip in with one initial question, which is, I mean, one thing I got from that is going all the way back to the Jurassic, you essentially seem to, you had the topography around the Central Asia region, which was somewhat similar to what it is now, right? Places that were deforming, places that were high, were, where we see the Tianshan now. You have places such as the Jungarian Basin and the Ili Basin, which seem to be largely undeforming. So there seems to be this long-running pattern of reactivation of some areas and non-reactivation in other areas. So I guess what I wanted to know, do you have any insight into why places like the Jungarian Basin itself, what is special about the Jungarian Basin, which means that it is not deforming like its surroundings are, and seems to have been repeated for such a long part of geological history?
Well, I guess most of the deformation is localized along the lithospheric structures, so the big weakness zones inside the range. And we are used to see the quaternary topography as a very steep mountain ranges and so things like that. But most of the time, I guess this region remain flat, and even more flat than what we know now. If you've been to Kazakhstan, I think most of Central Asia was looking like Kazakhstan. If you talk about Jurassic mountains, I would compare them with the Karatao Ridge, for example. So a few hundred meters high, maybe a kilometer or so, with flat tops, and not a lot of sediments produced from that. And I think most of the deformation is localized on previous zones or weaknesses in the crust. And the interesting part is that we remain in a generally semi-arid climate for about 200 million years, and that helps preserving the surface through the various orogenic events. So, yeah.
Okay.
I don't know if that answers the question, but I always describe Central Asia as a flat area.
Yep.
And quaternary is just an artifact.
Yep. Yeah. Everything increased in that time. Yeah, for sure.
Yeah, sure.
Yeah,
and even in the Cretaceous, I guess we have a reactivation of the topography, but it must be very, very limited in very small mountains.
Okay. Thank you. Okay, so we have one question in the chat that's been typed in. So did the Northern Tertium and Jungar basins develop in the Cenozoic as flexural basins? And what was the main reason for the Mesozoic subsidence in these basins?
Yeah, they are clearly flexural basin in the Cenozoic, that's for sure. All the depot centers are localized along the main ranges. So Western Kunlun, South Tianshan and North Tianshan. The Mesozoic subsidence, it's more difficult to understand that. It's especially difficult in the Jungar basin because the tertium is just a sag and the subsidence there is very limited, which is good because we don't think we have a lot of deformation. But indeed, the North Tianshan, the North Tianshan and South Jungar looks like a flexural basin. And this is probably linked, I think, to the nature of the basement. We have not a lot of indications on the nature of the Jungar basement. And it's probably a difference in the basement. So we allowed easy subsidence of the Jungar and no subsidence of the tertium. But this remains a mystery for me. The discrepancy between the two, the difference between the two basins in the Jurassic.
And I think that's probably in some ways connected to my question. We don't really know what the basement of the Jungarian basin is. And yeah, there's just nothing, no information really. As
far as I know, no.
Yeah.
You have 10 kilometers of sediments on top. So it's not easy.
Yeah. Okay. So next question then from Magali. Thank you, Marc, for the great talk. Two questions about the timing. One, when occurred the inversion from the normal sinistral motion to the dextral motion along the Talus Vagana fault? And then I'll read out the second one as well. We'll take this over. Two, you have nice and large triangular facets showing a large cumulative offset. My question is, since when and what are the role of these normal faults? Okay, so first of all, when did that change happen on the Talus Vagana fault? Second, can we constrain when that normal faulting occurred within the central within the interior of the Tianshan?
Okay, first one, as far as we can date the equivalent of the Kalazar formation all around Tianshan, we think this occurred probably in the very late Jurassic or very early Cretaceous. But because these are sediments deposited in arid environments, we have no pollens there, or nearly no pollens, so they're very difficult to date. But altogether, I would say at the limit between Jurassic and Cretaceous, which is slightly before the docking of the Lhasa block. So we don't think the Lhasa block is responsible for the inversion of the basin. And the only driving mechanism we see is a change of dynamics along the subduction zone of the Neothetis. We don't know why, but maybe we assume the back rolling is stopping or something like that. And we see also the same sort of inversion in the Kopedak, for example, and a little bit in Kizilkum, where we increase the strike slip faulting. For the second one, triangular facets, yeah. Well, let's go there, Magali. In fact, the Yili Basin is thought to have been a pull-apart basin in the late Carboniferous, early Permian. And I think what we see here is just a reactivation of those faults, maybe in a strike slip pull-apart setting. But I'm not sure. There is clearly a very strong strike slip faulting on the Narat fault, but it's also normal. And on the other side of the Yili Basin to the north, we also see normal faults. So probably a strike slip movement inside the range, I guess.
Good, thank you. So now John Suppe also says, very interesting overview. What are your thoughts on the timing of the late Cenozoic activation of the Tianshan and northern Tibet? The
timing of the late Cenozoic, I would say, from what we've seen with the fission tracks and with the sediments inside the Jungar Basin at least, I would place a very strong uplift around 10 million years, the onset of strong uplift around 10 million years. We have evidence of vertical movements starting in the Oligocene around, I would say, 30 million years or so like that in the Tertium Basin. but in Junger, it's definitely around 10 million years, more or less, maybe 2 or 5 million years. But yeah, and everything is concordant. We see the lake disappearing. We see the alluvial plain starting to be fed with coarse sediments. All the fish and track ages are around that time too. I would say 10.
Okay, thank you. Any more questions? Okay, and just to follow up from John, very interesting. Southwest Tarim Fletcher also gives us 10 million years, I think.
Yeah,
so,
all is concordant. But this is a general event in all the Tibet and Tianshan region. We also have fish and track ages of 8 million years in Kunlun, for example, or in the Tianshan. The Altunshan activation to the south is also around 10 million years. So there is something happening there at that time. And it's a widespread event.
I've often wondered whether you see, because you've got something starting earlier, 30 million years or more, and then you've got the 10 million year thing, and whether you see any pattern. Do you see like a widening of the deformation zone at 10 million years? The northern Tianshan parts starting, which were actually kind of not really deforming before, but you had the core of the Tianshan, the high Tursky range, things like this that were maybe active at earlier times. I don't know if there's enough detail to be able to say that or not.
Clearly, what we think we see is a first activation of the main lithospheric, the main strike-slip faults. For example, we have evidence of activity on the Alkintag fault around 45 to 50 million years. Mm-hmm. We have the Narat fault around 55 to 50 million years. It looks like we are reorganizing some of those blocks along the main strike-slip fault first. Mm-hmm. Then still things start to be blocked, and we start to deform slightly the block. So we do shortening. That starts around 30 million years, and then it increases around 10. Okay. But yeah, it's first it's a first shock. Then we start to block the blocks, and then we deform them maybe from 10 or a little bit earlier. Okay. Okay. But yeah, it's a continuum, I would say.
Okay. We have one other question from Magali. How do you explain no motion between 66 and 35 million years in a geodynamic point of view? I guess what was not happening in order to why do you have that first shock and then things happening at a later time?
66 to 50 is probably because we're not accreting India yet. We are accreting small blocks like the Khoistan or the Dras or the Elmen block, for example, to the west. So we have the first shocks, and the main one is coming later. But as I was just saying, the first deformation is just a reorganization of the main lithospheric blocks before we start shortening them. And the shortening is clearly after 35, and it increases around 10. Yeah, but it's a sequence of deformation. It's like crushing two cars, one in the other. You first deform the bumpers, and then you start deforming the whole cars.
Great. We have a question from Feng Chen. Great talk. Thank you, Marc. A quick question. What role did climate play in the growth of the Tianshan during the Mesozoic and Cenozoic?
I think because we have very semi-arid to arid climate, we are not eroding. So we preserve the previous topography, and we limit the uplift because we don't remove material from the range. So I would say it impeded uplift rather than inducing uplift. If we had a very humid climate, like for example the Longmen Shan or the Himalayas, we see those big peaks going up very fast. It's not the case in Tianshan. We remain with a very non-steady state topography. That's probably because of climate.
Yeah, very interesting thought, actually. Yes, good point. Look, we're coming up to the end of the hour. I aren't seeing any other questions coming in. So this is probably a good time to end the lecture, and just to thank Marc once again. It was really interesting. I learned a lot. I think everyone did. And this is going to go online again, so you people will have the opportunity to go through this themselves later time. And then please, all of you, tune in for the next one when we restart in the autumn. Thank you very much.
Okay, thank you very much to everybody, and I'm happy to discuss any point with any of you by email or whatever you want.
Great, thank you.
Okay, bye-bye.
Bye-bye.